same update statement, same row, same table runs in 3 milliseconds this morning, 400 milliseconds this afternoon. Nothing changed. You're the only user, no schema changes, no new indexes. The row is still there. It's just somewhere else than you think. The reason is the single most important fact about how Postgres stores your data, and almost every quirk in the rest of this series comes back to it. To see it properly, forget the SQL abstraction for a moment and look at what a table actually is on disk. A Postgres table is a file. That file is chopped into fixed-size chunks called pages, 8 kilobytes each. Every page holds a header and then as many rows as fit. Postgres calls those tuples. When you insert a row, Postgres finds a page with room, writes the tuple into it, and remembers where. A row's physical location is a page number plus a slot within that page. Now, the fact everything hangs on. When you update a row in Postgres, it does not modify that row in place. It cannot. Instead, it writes a new copy of the row with your changes applied somewhere else and marks the old copy as no longer current. Both versions now exist in the table. The old one is called a dead tuple. It's still on disk. It's still taking up space. It just isn't visible to new queries anymore. Delete does the same thing, minus the new version. It just marks the existing row dead. Update is really insert a new one and mark the old one dead in one atomic step. This design has a name, MVCC, or Multi-Version Concurrency Control, and it exists to solve a real problem. Consider the alternative. If Postgres modified rows in place, then the moment a writer started changing a row, a reader either has to wait, gets a lock error, or sees a half-changed row. Every long report you run would block writes, and every write would block reports. Databases that work this way spend a lot of engineering time trying to hide that from you. MVCC's answer is different. Because old versions of rows still exist on disk, a transaction that started 10 seconds ago can keep rating the table exactly as it looked 10 seconds ago, even while 100 other transactions are updating rows out from under it. Each transaction gets its own consistent view of the world, its snapshot, and reads against that snapshot no matter what anyone else is doing. Readers never block writers, writers never block readers. Nobody sees half-finished changes. It's a genuinely elegant piece of engineering, and later episodes in this series show exactly how it powers safe concurrent access when two users try to buy the last item at the same instant. But it has a cost, and the cost is what makes your afternoon update slow. Every dead tuple is a row Postgres still has to walk over when it scans the table, even though no query will ever return it. Every dead tuple takes up space in a page, and every dead tuple counts against how many live rows fit in the same amount of disk, because pages don't get compacted automatically as rows die. 2 pages side by side. Left, labeled morning, a page mostly full of green live tuples with 1 gray dead one. Right, labeled afternoon, the same page now mostly gray dead tuples with a few green live ones scattered through, captioned, same page, more work to scan. Play forward what happens through a normal day. The users table starts the morning clean. Someone runs a job that updates a status column on every row, 1 million updates. Postgres now has 2 million tuples in that table, 1 million live current rows, and 1 million dead old versions sitting in the same pages. Your afternoon update, which needs to find one specific row, is now walking through twice as many tuples to get to it. The row itself is fine. Everything around it is corpses. This is what bloat means when you hear Postgres people complain about it. A bloated table has far more tuples on disk than it has live rows, and every operation against it pays for that difference. So how does Postgres ever get rid of the dead ones? a background process called Autovacuum. It periodically walks tables, finds tuples that no active transaction can possibly still need to see, and marks their space in the page as reusable. Not deleted, reusable. The next insert into that page can put a new tuple in the slot where a dead one used to live. Notice what Autovacuum doesn't do by default. Shrink the file. If a page ends up completely empty, the file on disk is still the same size. Those empty pages just sit there, ready to hold future rows. Getting the file physically smaller requires a more aggressive operation called vacuum full, which rewrites the whole table and takes a heavy lock while it does. Which is why most teams live with slightly bloated tables rather than run vacuum full on a live database. Autovacuum runs on a schedule tuned to how quickly a table is changing. When it keeps up, everything's fine. Bloat stays low, queries stay fast. When it falls behind because the table changes faster than the schedule expects, or a long-running transaction is holding old versions possibly still needed, or someone tuned Autovacuum to run less often, dead tuples accumulate faster than they get cleaned. Bloat grows, queries slow down. That's your afternoon. And here's the callback to the funnel, if you watch that one. This is the same mechanism behind delete 10,000 rows, and the table gets bigger. The rows aren't gone, they're marked dead. Storage only comes back after vacuum runs, and only into that same file, never back to the operating system unless you rebuild the table. There's one more consequence of every update writes a new row that trips people up, and it matters for the next episode. Because the new version of a row lives in a different physical location from the old one, every index on that table now needs to know where the new version is. Indexes point at physical row locations. Update a row, and every index, the primary key, every secondary index, every unique constraint, potentially gets a new entry too. Every write is not just a write to the table, it's a write to every index that references the changed columns, plus, in many cases, all the others. Which is why just add an index, the reflex the funnel opened with, is not the free win it sounds. An index makes reads faster. It also makes every write slower, and every dead tuple stays visible through those indexes until Autovacuum catches up. That's the whole subject of the next episode. So what actually made your afternoon update slow? Not the row, not the query, the tuples surrounding it, a million dead copies of rows that used to be there, all sitting in the same pages, all making the walk to the one row you cared about longer than it needed to be. The row is exactly where it was this morning. It's just that afternoon Postgres has to scroll past a lot more corpses to reach it.